Yes, always.
Start well, other people. Then, yeah, so today it's my pleasure to welcome James Beattie. So he has a joint appointment between CETA, University of Toronto, and Princeton, and today he's visiting us from Princeton, right, which simplified his travel quite a bit. And in the summer he's moving to Institute of Advanced Studies for postdoc. He received his PhD in 2024 from Australian National University, and at the same time he was also a Fulbright fellow, so he spent quite a bit of time at UC Santa Cruz. Research interests of James are everything related to turbulence and dynamo on a range of scales, from Earth magnetosphere to ISM to plasmas around compact objects, so I'm sure you can find connections. So please sign up to talk one-on-one with James, and yeah, please welcome.
Thanks so much. So today I want to talk to you about a really interesting story, I think at least, which is about how you can drive turbulence in a galaxy with supernova remnants. And really what I want everyone to take away from this is the ideas that Kolmogorov had back in 1940 about driving of turbulence on large scales, trickling down to small scales, forming some kind of viscous scale that is then thermally truncated, are just kind of not relevant that much for galactic turbulence, even though if you're in the ISM, we kind of think of the galaxy this way, we apply it all the time in our models, it's just not the correct model for galactic turbulence. And this work really is kind of a contribution over the last year or so from these 3 studies. The first one called So Long Kolmogorov, which I think is very fitting for my talk, and then talking about universality of turbulence in different disk galaxies, and also this last one in 2026, where I really nailed down the mechanism for how turbulence works in supernova remnants. So the roadmap for this colloquium, if we want to talk about Kolmogorov turbulence, I have to discuss what that actually means. So I'm going to kind of go through in a bit of a hand-wavy way what Kolmogorov turbulence is, and I'm going to be a little bit pedagogical here, so you're going to see some diagrams. We're going to have to do a little bit of math, so I hope that's fine with everyone. Then I want to go into really what it means to be driven by these nuclear explosions, supernova-driven turbulence, and how this might fit into something like your standard Kolmogorov cascade. I'll talk about spectra, I'll talk about cascade directions, and then I want to finally talk about if you're just blowing up, if you're just exploding in the galaxy, where the actual incompressible turbulence comes from. So these are the 4 things that I want to talk about in this colloquium. I hope that makes sense. So the ISM, just for those who are not familiar with the interstellar medium, it's really a laboratory for interesting nonlinear physics. Even though it's very hard to probe these nonlinear physics with observations, the ISM is itself this beautiful lab that has all this nonlinear physics entrenched inside of it. So it's a multiphase transistor supersonic compressible plasma. It has very high Reynolds numbers. We'll talk a little bit more about Reynolds numbers in a second. But what this means is that it's highly turbulent, it's highly nonlinear. It's driven by a zoo of sources, gravitational instabilities, supernova explosions, stellar feedback, et cetera, et cetera. It's pervaded by ultra-relativistic particles, and these really peak in the GeV-TeV range. So these are, of course, the relativistic cosmic rays. It's full of actually non-Gaussian density structures. So it's really not your standard plasma that is kind of weakly incompressible and blah, blah, blah. It has these extreme non-Gaussian gas density structures, and these are deeply related to how it forms stars. These are ribbons, striations, sheets. These are structures that are log normal, so you take the logarithm of the mass density field and it looks normal, but they're really high non-Gaussian in regular linear space. And it has a dynamically important and maintained magnetic field. Now today, in this first talk, I will not be talking about magnetic fields at all, so this is a bit of a shame. You'll have to come into my luncheon talk to actually discuss magnetic fields with me. Now let's talk about turbulence in a somewhat hand-wavy way. So we should start with the momentum equation. This is just the most boring vanilla equation you can kind of construct in fluid dynamics. It really is describing the momentum conservation of a fluid element. What's a fluid element? Well, it's the moments of an underlying plasma distribution function, and it gives you some mass density of the underlying plasma. It gives you an internal pressure of the plasma, and then the momentum of this fluid element is governed by this equation. This equation has a number of interesting features. Written out like this, not many interesting features, but just 2, I would say. And I'm going to use this, this notation probably throughout the colloquium a little bit. And this, of course, just is a UI-UJ tensor operation like this. Really what I want to get at is that there are 2 interesting things here. There's this thing, which is like, a u squared. So this is a nonlinear thing. This is nonlinear. And there's this thing, which is the viscosity. And the kind of way to think about these 2 interacting forces is that this one creates nonlinear structures and this one smooths out nonlinear structures. So we can just take the ratio of these 2 things and we get something called the Reynolds number. The Reynolds number really is the ratio between how much I can create nonlinear things in the fluid versus how much I can smooth nonlinear things out in the fluid. And now you're probably all familiar with the Reynolds number, just going like this. Well, this is the dimensional prescription of the Reynolds number. Really, the Reynolds number is this. It's the ratio between these 2 terms in the Navier-Stokes equations. Now you can ask the question, what is the Reynolds number in a galaxy? Of course, the galaxy is a multiphase medium, so it means that the viscosity is changing as a function of temperature. But at the end of the day, for the warm ionized medium, you get Reynolds numbers of 10 to the 7. Warm neutral medium, 10 to the 7. Cold neutral medium, as you go to the colder phase plasmas, the viscosity is getting smaller and smaller, and so you get higher and higher Reynolds numbers. In other words, we are in always the very nonlinear regime, no matter what phase you're in the galaxy. This is interesting because it means, now I'm thinking about grabbing the entire galaxy and perturbing it, hitting it with kind of what wave mode. I just want to understand what this wave mode will do on the outer scale of the galaxy. Well, we can go back to our nonlinearity. This is just the nonlinearity that we saw before, and I can grab 2 different waves and I can essentially just put them through the nonlinearity, and you can see just through momentum conservation, so this is the wave vector of my first mode, the wave vector of the second mode, birthing a new wave vector. This is the child mode of these 2 parents. Just through momentum conservation, this K3, this third mode is going to be the summation of the 2 modes before it. So what does that mean? Well, it means that essentially when you mix the wave modes together in the nonlinearity, you birth a new wave mode that is higher in spatial frequency. So essentially, how to think about this? Well, it means we go from here to here. If the nonlinearity is strong, we're essentially birthing new wave modes that go to smaller scale, higher spatial frequency, shorter wavelength. So this creates, in other words, this nonlinearity to a twiddle essentially creates new wave modes that are higher frequency wave modes, and it does it on the nonlinear time scale of this operator, and for the outer scale of the galaxy, this is like a giga-year time scale. So this is just generally what a nonlinear plasma will do. You can keep playing these games, and of course you can keep playing these games. It's going to just keep birthing new wave modes, new children wave modes, and this will just keep happening if the nonlinearity is strong. Now there's something else I should point out about this nonlinearity. When you expand it, you just do your, year 2 vector calculus class, you can see that this nonlinearity actually contains essentially an isotropic pressure term. So this is just like the pressure term, the contribution from the velocities that are contained in this nonlinearity. So actually for the astrophysicist, what this nonlinearity gives you, it gives you a turbulent pressure. It gives you a turbulent pressure on every single length scale the nonlinearity is strong. So this is why this is interesting for star formation folk. I also just want to show now this pretty picture. So we're describing this situation where we're just birthing new and new wave modes. So the wave modes actually should create some kind of self-similarity. So there should be some self-similar process in the power that the wave modes are getting. And that means that if you measure the statistics, in this case it's actually like a column density statistic, you should expect that there's some kind of fractal structure as the wave modes on top give rise to more and more children wave modes in a self-similar kind of manner. And this is exactly what we see. So here I'm showing you the LMC. They've kind of cut it into patches. This is just like a column density map of the LMC, cut it into patches and computing the power spectrum of the LMC. The power spectrum is indicated for each patch on the left. I'm just zooming into one patch. And my interpretation of this, I know it's a little bit hand-wavy because we're looking at column density rather than velocity, and the turbulence really is in the velocity. But what you're seeing here between 1 kpc and 10 to the negative 2 kpc is you just have this beautiful self-similar structure in the density, which my interpretation is that we're looking in the middle of the cascade, in the middle of the turbulent cascade. Now you just keep playing these games until the Reynolds number becomes essentially small enough such that the nonlinearity truncates. And by that I mean the Reynolds number itself depends upon scale, so you can write down the scale-dependent Reynolds number, and at some point the Reynolds number becomes 1, and you have diffusive processes essentially overtaking the nonlinearity. But on quite small scales, and I'm talking about 10 parsec scales, we get some other beautiful structures that presumably arise from the turbulence. One of them is Larson's law. So this is actually now the velocity dispersion as a function of length scale. And what you're seeing is a collection of molecular clouds, molecular clumps. And you're seeing their molecular line, their non-thermal line broadening, and you see that it follows this beautiful L to the 1/2 relation. And this you can actually get at just through a turbulence theory. So it seems like the galaxy is organized in a fashion that actually has the turbulent cascade imprinted onto it. Very, very cool. Now we think that this cascade is large, so we think it goes across many, many scales. Here I was showing you essentially just picking out the random cold clumps of plasma in the galaxy. It follows this beautiful scale-dependent relationship between the velocity dispersion and the length scale, which looks like essentially supersonic turbulence. I'll talk a little bit about this in the luncheon. We go to even smaller scales, so smaller scales and larger scales, and we take actually the electron density, so just the electron density, and what you find is this huge power law in the sky. This is, I think they call it the grand power law in the sky, or there's another word for it, the grandest power law in the sky. There's a series of papers that were making grander and grander power laws. And essentially this whole thing from I think it's actually like a couple of kpc down to, like, I think this is 1 over meters. So what is this? This is very, very small scale. This is a beta right here. It just follows this k to the minus 5/3 power law, which I'll show you in a second, looks like Kolmogorov turbulence. So we think that turbulence is actually imprinting itself on all of our statistics in the galaxy. Why should astrophysicists care? I'm not going to talk about this too much. I hope everyone just cares, because turbulence is a component of a galaxy, so we should be able to study turbulence as it is. But I also want to talk about, it matters a lot for star formation. Like this beautiful study by Donghee Nam was changing the turbulent power spectrum from k to the minus 2 to the k to the minus 1, and essentially showing that the entire IMF has a different high mass tail depending on what power you prescribe to your turbulence. So really it's changing the nature of turbulence support on small scales, which changes the nature of how the gas fragments, which changes the initial mass function of stars. Now, of course, if you're into cosmic ray studies, I won't need to give you a lecture on why turbulence matters. There's really two competing ideas for how cosmic rays are scattered through either self-confinement or extrinsic turbulence. Both of these properties, especially extrinsic turbulence, are determined by the turbulence. So you can't really get away, if you're thinking about cosmic ray transport, from the underlying turbulent background medium in which the particles are transported in. Now let me talk about two great insights from Kolmogorov. I've started already using the language of Kolmogorov turbulence, but I haven't told you what that means. So I want to just go through this very, very briefly. So Kolmogorov was thinking about, you have a hierarchy of scales, and that these modes should actually talk to each other with a constant energy flux between all the modes in the hierarchy, between all the different scales in the turbulence. So this is one assumption, that this energy flux on each scale is constant. He didn't consider magnetic fields, boo, and there was no background density inhomogeneities, so this is an incompressible kind of idea. And also the statistics are isotropic, so if you're looking through any line of sight around in K space or in L, everything looks exactly the same. Now you can just rearrange this constancy in energy flux directly into a relationship between the velocity dispersion on length scale L and the L itself, and it just looks like L 1/3. And this is kind of Kolmogorov's amazing idea. Just simply by going between the constancy of energy flux, you can integrate this. You can get the power spectrum. It goes like k to the minus 5/3. I do that in my next point. So this k to the minus 5/3 is Kolmogorov's big prediction. Now, we'll say that Kolmogorov predicted much, much more than this. He essentially predicted all orders of structure function. And what do I mean by structure function? I mean by this. Essentially, you can write down your power spectrum into something that looks like just a real space calculation between two different points. The velocity at x and the velocity at x plus L, where L is essentially describing the length scale of your eddy, and you're taking an average over all x, so you're essentially picking out all eddies. And this is really what we mean when we talk about these U as a L relations. We actually mean this structure function computed on L, and it goes like L 1/3 for the first order structure function. So you can raise this to any power here, and Kolmogorov has a prediction of every power of this structure function. That's what I was trying to say. Kolmogorov made more than a prediction than just the power spectrum itself. Okay, so something very cool that doesn't come up in the astro literature too much is this exact relation that comes from the Navier-Stokes equations and Kolmogorov's ideas, which really tells you about something more than just the structure function or the power spectrum. It tells you about the direction in which energy travels through the cascade. And this is the famous 4/5 law. So this is essentially a component of the structure function. This is the divergence of it. This is the gradient of the structure function, or the divergence of the structure function on length scale L. And it gives you this, a 4/5 epsilon. Epsilon here is an energy flux, so it's positive definite. And what this means is that the divergence, the flux of the cascade is equal to a negative quantity. So of course, the divergence, if it's negative, means it's going down. So it goes from large L to small l, or in other words, from low k to high k. And this tells you the direction of the cascade. It tells you that in Kolmogorov's world, the cascade goes from large scales to small scales. This is built into the theory. This is Kolmogorov's 4/5 law. It's very important because we're going to show that in some cases, this is not true. So when you put all these things together, what you have from Kolmogorov is a theory that is essentially described by energy flux coming in on large scales, so long wavelengths, and it goes down a cascade, k to the minus 5/3, all the way down to the dissipation scales. It travels like this. It goes down the cascade from large scales to small scales. I hope that's clear. I didn't really go through k-space. I hope everyone understands what a k vector is versus a length scale, et cetera, et cetera. Okay, so for galaxies, there is this fact. I think it's a fact that the galaxy we reside in is turbulent. This is just based on the Reynolds number estimates. But also that turbulence can be driven alone in terms of trying to match the energy density, the velocity dispersion of a galaxy on the outer scale with the energy injected from supernova, just from core collapse supernova, in fact. You can essentially get that the fluxes from the turbulence in the Milky Way galaxy and the fluxes from the supernova essentially give you 10 to the minus 2 in ratio. And so this means that you only need 1/100th of the energy from the supernova detonating in the galaxy to go into the cascade to drive a steady state cascade all the time in the Milky Way galaxy. So it's not a really stiff kind of bound here. This is easy to do. We can take 1/100th of the energy and put it into the turbulence. This is fine. We just need some kind of momentum energy efficiency factor of like 10 to the negative 2. The question that I pose is, does this situation where you're injecting energy into the galaxy via supernova look anything like this? Does it look like this idea that Kolmogorov is painting? So this is what we're going to go through. Now there are a number of things that could happen here, and I'll go through the number of things that I think, the different scenarios that could essentially that could be realized, and then I'll talk about the simulations that I ran, and then I'll talk to you about the results. So a little bit more hand-wavy stuff to begin with, apologies. But supernova detonate here. If there's a cascade, supernova detonate there. They're detonating at the small scales. So this is already a mystery. This already doesn't look like Kolmogorov. The driving is coming from there, so that's weird to begin with. So there's something that could happen. Of course, the supernova could expand. They could expand and interact, and their interactions could essentially describe a whole set of long wavelengths, large low K modes, and potentially the turbulent injection is through these interactions. So that's one thing that could happen. Another thing that could happen is they detonate here and they somehow non-locally couple to the long wavelengths. That could happen as well. There could be something about just jumping over all the scales and dumping it into the large scales. So there could be a mechanism that does this. They could couple on every scale. So they could actually be injecting energy on every single scale, and we're going to go through exactly what's happening and actually differentiate between these scenarios with the data. Or this could happen. You could essentially be injecting right here, where they detonate, and then you could have a cascade that goes up to larger scales. This could happen. This is an inverse cascade scenario. So how to test between these different scenarios? Well, you run simulations, and I'm going to do some fancy calculations to work out how the energy flux works. Now, I'm going to talk a little bit about these simulations. I think they're very simple simulations. This is actually going reverse in time right now and now forward in time. These are, blowing up, making nuclear explosions go off in a stratified medium. So there is some stratification. I'll talk about the stratification in a bit. This is the ITC Colloquium, so I'm going to talk a little bit about computations here. So this is my numerical model. It's just a hydrodynamic model. And you can see that it has essentially a mass source in my continuity equation, has a momentum source in my momentum equation. It has a gravitational potential that is actually fixed in time, so it's a static gravitational potential. It has a cooling function, and it has a energy injection as well from the supernova. So in other words, they inject energy, momentum, and mass. The grids that I'm using here up to 1,000 cubed. So what does this mean? It means that I trust about 10 grid cells, and below that, so these are 1 kpc in length scale. So one grid cell is 1 pc, and I trust about up to 10 pc in the simulations, just to give you an idea of what I trust in these simulations. The static gravitational potential looks like this. It has a disk, it has a spherical halo. Really, really very simple, and this is static in time, like I said, so this just gives me some background stratification. My supernova prescription is following a KS relation for this particular Milky Way analog galaxy. It's really very simple, but you get essentially 1 supernova per 100 solar mass of star formation, but there is no star formation in this simulation. This is kind of just the star formation rate that it would be for this Milky Way galaxy, blah, blah, blah. You get what I mean. So there is a cooling function, I said. So the cooling function is actually, it's actually solving a full network of a variety of species here. And essentially the cooling function is quite truncated at 10 to the 4 Kelvin. And this means that we have no self-consistent cold phase gas. And I didn't want any cold phase gas because when you're resolving only down to 10 pc everywhere in the grid, the cold phase, it doesn't matter at all. The cold phase looks like little diffuse clumps that don't actually contribute much, but change my integration timescales significantly. Now, this is what the phase plot looks like. So you can actually see that there's no self-consistent cold phase over here. And you essentially have this disk that sits at around 10 to the 4. You have a warm neutral medium that's been developed just through the adiabatic expansions of the supernova. You have adiabatic cooling below 10 to the 4. So these are all adiabatic processes. And then you have a hot ionized medium for the wind. So I hope this makes sense. So yeah, this is a nice hot wind at over 10 to the 6 Kelvin. Now we want to essentially work out if a steady state exists for this kind of galaxy, and indeed it does. So this is now showing how I integrate the galaxy as a function of turnover time. This is the turnover time calculated by the largest scale eddy in the simulation, and this ends up being around 80 megayears. And what I'm showing you here is the Mach number plotted volume integral over the entire simulation, and we integrate this. We go through essentially a burn-in phase where the galaxy is doing a bit of breathing, but it settles down, bubbles, 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 until we get into what I would call a statistically stationary state, and we do all of our averaging, all of our turbulence statistics in this stationary state. So this is kind of important for us because we want to average over a state that looks quite similar in statistics, just so we get better statistics for all of our measurements of the turbulence. Now I want to dive right into the spectral properties of the simulations. I hope I've given you enough breathing to understand what the simulations are. Now I'm going to tell you about the kinetic energy spectrum. And so I thought I had some, nope, okay. I want to talk to you a little bit about the kinetic energy spectrum, which is this top spectrum here. Already you can see that the total velocity, so this is the total velocity up here, this is the mode of roughly the scale height at the disk. You can see that the spectrum actually does not follow Kolmogorov immediately. It follows k to the minus 3/2. So already this looks like a deviation from the standard Kolmogorov theory, but who cares about spectra? Spectra are super degenerate. We have to go deeper. But the other thing that I want to show you is that when you actually break apart the velocities into the incompressible modes. So these are the modes that just cause vorticity, cause the turbulence, and the compressible modes, which are the modes that are being generated by the supernova remnants, these huge explosions happening in the disk. The spectrum look very different. So the incompressible mode spectrum looks like k to the minus 3/2, and the compressible mode spectrum looks like k to the minus 2. And this is kind of a spectrum of acoustic wave turbulence or the spectrum of shocks, or there's a number of different explanations one can evoke for a k to the minus 2 spectrum. But my main point here is that the life history of the incompressible turbulence and the compressible modes are different. We're going to see this come up. Now you can take the ratio between these spectra. Okay, so now I'm just looking at the energy that's in the compressible modes versus the incompressible modes. So here's the incompressible divided by the total power. And what you see is that there's a peak. There's a peak in incompressible energy, i.e. a peak in the eddies, the vorticity, the turbulence, happening at a particular scale. And this scale happens to be the wave number of the cooling radius of the average supernova remnants. So this is already very, very interesting. Are we seeing a driving scale of the turbulence on these really small scales, scales of order 14 parsecs? Maybe we are. So this paper and a collection of these spectral results were all done by Izzy Connor. She's a fantastic undergrad at UCSC, also an ex-Olympic athlete. So in mentoring her, I've become an Olympic turbulence coach. But what is very cool as well is you can essentially grab the incompressible mode spectrum and you can compare it with the sound speed spectrum. The way that I want you to think about the sound speed spectrum of a turbulent disk galaxy is essentially tracking the temperature fluctuations, right? Because the sound speed is just the square root of the temperature. So we can essentially go between thinking about sound speeds and thinking about temperatures. But you can write down a very, very simple relation. If the sound speed spectrum is just essentially getting changed adiabatically, by acoustic modes, just by weak compressions all through the turbulence, you should get this linear relation between the sound speed spectrum and the compressible mode spectrum in the limit that everything is very adiabatic. The cooling doesn't matter very much. And this is what you find. You find that the sound speed spectrum should go like k to the minus 2, and it really does. So in other words, on average, these disk galaxies are really very adiabatic. You get locally, you get into a strong cooling regime, but globally, the entire phase of the galaxy is being controlled by the compressible modes of the turbulence. Now we essentially compare between different galaxies, Milky Way type galaxy, starburst type galaxies. And the coolest thing here is that you can normalize the spectrum by the scale heights. So we normalize the K mode here by the scale heights. And then we normalize the power by the power at the scale heights. And you can combine multiple galaxies together. You can combine them into something that looks like a universal velocity spectrum. It doesn't matter what phase you're in, if you're wind dominated or disk dominated, so as you move this way, you're getting down deeper and deeper into the disk. The scale height is, of course, right here, so really this is all disk, this is all wind. You can see that you get a universal turbulent spectrum, k to the minus 3/2. This k to the minus 3/2 really needs explaining, doesn't it? If you do the kinetic energy rather than the velocity, you break that universality. You actually see the imprint of the disk. And you can see a k to the minus 4/3 spectrum as you go down deep into the disk, and a k to the minus 1/2 spectrum as you go into the winds. So there is universality in this galactic turbulence, but it's in the velocity spectrum. It's not in the kinetic energy spectrum. Now, I told you we have to dig deeper into the turbulence. We want to understand things like, what's the direction of the cascade? Is it truly going from long wavelengths to small wavelengths, large length scales to small length scales? To do that, we compute these things called transfer functions. And I don't want to bore you with the mathematical details here, but really what I'm doing is I'm going into the spectral space, I'm grabbing a K mode from here, I'm grabbing a K mode from there, and I'm interacting them together in an intelligent way that probes that nonlinear interaction I talked about that we define the Reynolds number with. And I'm computing the direction of the energy flux and how much energy flux each mode pair has with each other. I hope this makes sense. I'm not going to bore you with this. But really what I want to try to highlight here is that we have the compressible mode spectrum, the incompressible mode spectrum, and I'm able to probe all the interactions between the modes in each spectrum and between each spectrum using this mathematical tool. Now, we have to do a little bit of interpretation because this plot gets a bit crazy. Now, one thing that we should look at is the energy flux as a function of scale. So this is the total amount of energy moving through the modes as a function of scale. And for the Kolmogorov prediction, for the Kolmogorov idea, it should be constant in the inertial range. And this white line comes from just simple turbulence boxes. This is kind of what you get in simple turbulent boxes. You can see it is roughly constant. Even this turbulent box is not quite constant, so Kolmogorov maybe is a little bit wrong already. But in the simplest case, this is what we're looking for. We're looking for a constant energy flux. Now, instead of just integrating over the energy flux moving out of the modes and moving into the modes, I can actually compute all the energy flux between two modes. And this is called the shell-to-shell transfer. And for a shell-to-shell transfer that is local, as in neighboring modes are talking to each other, and is direct, i.e. going from large scales to small scales, it should look like this. So you should look at the diagonal mode right here. So this is a Q mode, this is a K mode, if we're trying to interpret this. And essentially, the mode is leaving this, so the blue, the energy flux is positive, it's leaving this, it's going into the diagonal mode, then that diagonal mode is giving its energy flux to the next mode over. And it does this like this, so beautifully local, all the way down, all the way down, all the way down, all the way down to the dissipation scales. And this is coming from my 10,000 cube simulation that was published in Nature. This calculation took me a year to work out during the time where we didn't have AI software programming tools. Now, let's look at it for the supernova case. This is where it gets really interesting. So there are two different transfer functions I'm showing you here. I hope this was enough to help you interpret what a transfer function should look like in a standard turbulent box. So you essentially have a cascade that goes from low wave numbers, large length scales, down to higher K, smaller length scales, and it looks local. There's this local talking. All the modes are chatting to their neighbors, they're giving energy to their neighbors. This looks very nice and friendly. Now we go to the real case. You see already that you have these big tails coming off once you get on larger scales into the winds. And this is for the three-wave interaction between all incompressible modes. So this is kind of like the Kolmogorov kind of cascade, full of non-local interactions on large scales. As you get to smaller scales, indeed, you do find that the local interactions dominate and that you have a cascade that goes this way, that goes that way. But now let's look at a different set of mode interactions. So this is from incompressible to incompressible, mediated now by a compressible mode. Now we see something very distinct in this plot that we could not see in the standard turbulent boxes, and that is that there is this beautiful inverse cascade. You can see a direct cascade on small scales where the blue is on top, the red is on bottom, and then the energy flux flips. It flips now with red on top and blue on bottom, which means the cascade is completely flipped. It's going from high K to low K, i.e. small length scales to large length scales. Where does the flip happen? It happens just as we saw the peak in the vorticity. It happens right at the cooling radius of the supernova. So some kind of physics is happening at the cooling radius that is essentially sending modes to large scales. This is quite cool. Now you can actually go into Fourier space, grab the modes in the inverse cascade, and then inverse Fourier transform them back into real space, and you can actually see the modes with your eyes that are causing this inverse cascade. So I'm now just plotting a spatial slice through the simulation, through the disk actually. So in other words, the potential is pointing out of the page here, and we're kind of slicing through the midplane of the disk. You can see that these bubbles are supernova remnants, and you can see that when it's red, when it's brightly red, you have inverse cascade, and when it's deeply blue, you have direct cascade. So in other words, you have these young supernova remnants that are deeply red, that are, maybe that are essentially the sources of this inverse cascade. You have these older remnants, you can see here, that are actually deeply blue, that actually drive a direct cascade. But the remnants themselves, they also have big blue regions, and this is kind of in the post-shock region on the merger. There is some direct cascade also inside the remnants themselves. But this is already quite fascinating, I think at least. I'm taking a different slice here. This is the midplane of the galaxy here, and you can see that you get all this inverse cascade. Again, essentially flying up into the winds of the galaxy. So that there is a contribution of the turbulence of just getting material into the winds just through a cascade, through an inverse cascade from small to large scale. So in other words, the scenario 3 that we talked about is actually realized in the supernova-driven case. There is actually a legitimate inverse cascade from some driving scale, it ends up being roughly the cooling radius, up to larger scales into the winds. So this is very interesting to begin with. Now the cascade itself, so now you're seeing a plot of the velocity dispersion as a function of time in the galaxy, normalized by the RMS. And I'm just showing you some slices of the cascade at each one of these time realizations. So you can see now that these shell transfer functions are very useful because we can just see the cascade, right? We can see the mode-mode interactions in the turbulence. We can see the cascade with our eyes. You can see that the cascade is rather stochastic. It's intermittent. It comes and goes in the galaxy. It's not there all the time. It's not something that's always in the background. It's really coming and going. And it actually is coming and going with the extreme events in the velocity dispersion. You can see it gets very disrupted sometimes. Now, let's talk about where this incompressible turbulence comes from. We are driving with blast waves. Why does a blast wave control or contribute at all to the vorticity, to the incompressible turbulence? And why is it actually more than the compressible mode energy? It's much more. It's almost 90% of the total energy in the galaxy is in the incompressible turbulence. And yet we are driving with nuclear explosions, with blast waves. It's really quite strange. So we go back to our momentum equation, okay? And then we're going to take the curl of this equation. The curl of the equation is going to give us the vorticity, and you can immediately see that these terms, when I take the curl of them, will disappear. This one, because it's just isotropic, it's just an isotropic contribution at some radius where the supernova gets exploded upon. And this one, because it's a gravitational potential. When I take the curl, I don't get any vorticity from the two source terms I've added to my hydrodynamical equations. So I'm going to do a little bit more than take the curl, so please try to follow along. I'm going to take the curl, I'm going to take the Fourier transform, and then I'm going to square the equation. And this will give us actually a better idea of what's happening in the way that the turbulence generates from these source terms being turned off. Now I can write down, and I don't want to explicitly go into what this operator is, but I can write down essentially cascade terms for this vorticity. So those are all the cascade interactions that take energy from a vortical mode and give it to another vortical mode. And I can write down a source term. And the only source term here is actually coming from the equation of state. It's coming from the equation of state. It's essentially this grad rho cross grad p operator. So this is what we'd call baroclinicity. And it comes from misalignment between density and pressure. And essentially it's donating energy into the vorticity. Omega is the vorticity, the curl of the velocity field. And then I also have the sink term. We don't really have to care about the sink term. The interesting part, the important part here, is that the only source of the turbulence comes from this weird baroclinic operator. Now, do we have baroclinicity in our simulations? You bet we do. And it happens, the baroclinicity is turned on exactly at the cooling radius of the supernova. Why is it turned on at the cooling radius of the supernova? Well, because this shell, this is the baroclinicity that I've drawn on here. This shell, this is the contact discontinuity in the supernova, is actually going unstable. It's actually going thin shell unstable, which looks like a Rayleigh-Taylor instability. And you can imagine the pressure gradient is this way, and the thin shell is this way, so you have misalignment everywhere as you go around this fractal layer in the cooling radius, at the cooling radius of the supernova. So now it looks like we've identified why the cooling radius is so important here for the supernova. It is the radius in which the instabilities in the thin shell are kicking on. They have to kick on at the cooling radius. This is where the thin shell is, the whole supernova is expanding until it gets to its cooling radius, and the baryonic layer around goes really thin because it undergoes catastrophic cooling, and then it goes unstable. So the cooling is actually very important here. Now I can do some more quantitative stuff here. I can compute the other vorticity terms that might contribute. This is vortex compression, vortex stretching, baroclinicity, and you can see that this is, what is this? This is 3 orders of magnitude larger in baroclinicity than any other contribution to the turbulence. The baroclinicity is driving the turbulence here. This is what the baroclinicity looks like as a function of a slice. This is the plane of this is the galactic disk right here. You can see again the baroclinicity is just lit up everywhere at the supernova remnants where it's undergoing this intense cooling and instability. And as I say, it can be 5 orders of magnitude stronger than any other baroclinic source. Okay, so this gives us some ideas for what we should do with this equation, this rather complex equation. We should actually just ignore everything and only think about cascade. So this is our incompressible mode cascade and source. That's all we need from this equation, actually. And I'm going to use the shorthand notation P omega B for this entire term. Okay? Now, I want to actually test or understand if there's any relationship between this term and this term. I want to get at something analytical here. I'm not happy with just these correlations between terms and these pretty pictures. I'm very happy with the pretty pictures, to be fair, but I want more. Now, to do that, I go into my simulations and I grab every supernova remnant, and I define a patch around them. And then I have all of these supernova remnants stored locally, and I can do all of my local analysis at the remnant scale. And this, you're seeing a catalog of maybe a quarter of the supernova remnants that I've used here. And I'm showing you here essentially the baroclinicity in blue and the vorticity, the incompressible turbulence in red. And we're kind of switching between those two things. So you can see that this thin baroclinic layer here, the unstable thin shell, has this beautiful, essentially, atmosphere of turbulence generated around it. I really like this plot. Now, I already showed you that you can essentially do this, right? You can just equate the baroclinic term, the source term, with the cascade term. So I'm going to do that again. I'm going to play some games here. I can essentially work out that this term over here, I can write it down as the incompressible mode spectrum itself. So I'm not going to go through that, but people can ask me if they want to interested. And then I find a relationship between, an analytical relationship between the source term and the incompressible mode turbulence spectrum. And this relationship is only true if it's truly all the turbulence is just driven all by baroclinicity, if all of the turbulence comes from the baroclinicity. And I make this plot here. I make the plot of the two spectra. And if this relation holds, then these spectra should lay on top of each other. And in the inertial range of the turbulence, they exist exactly on top of each other. So this is beautiful. Already, it's suggesting that the baroclinic generation is controlling all of the incompressible turbulence. Exactly, just all of the incompressible turbulence come from the baroclinicity. Now I can compute the spectrum itself, and I can also see that the spectrum at the scale of the supernova remnant goes like k to the minus 3/2. And this should be very familiar to you by now because the spectrum of the entire galaxy is going like k to the minus 3/2. So in other words, it seems like there is a relationship between the supernova remnant scale spectrum, the turbulence generated at the supernova remnant scale, and the global velocity spectrum, the global velocity spectrum of the galaxy. Now, can we get an analytical model for this spectrum, right? It feels like the missing piece, k to the minus 3/2. Where's this coming from? We know that it's being fed by this unstable layer. We don't know why k to the minus 3/2. Well, we have to talk about the instabilities that are happening in this layer. This is what's important to us, is the instabilities happening in this layer that cause every corrugation, every fold in the layer. And then we're just looking at the misalignments between all those folds and the background pressure gradient to generate vorticity of order, essentially that corrugation. So that's how we have to think about this problem. Now, very, very nice. You know, there's nice work back in 1983 by Ethan. He's done the thin shell instability, which it plays a role here. But the thin shell instability is fundamentally the RTI, the Rayleigh-Taylor instability, applied to a spherical shell, a spherical cooling shell. And really, the growth rate of these corrugations goes like square root k. Okay, 5 minutes. I'll be there. 5 minutes is good. So now I'm going to do something crazy, and then I'm going to say the nonlinear time scale associated with the growing, is directly associated with the growth of these modes. So as in the cascade time scale, is directly associated with the growing of these corrugations, okay? So this is an assumption, but what happens? I'm going to assume that the energy flux is constant, and then I get exactly my k to the minus 3/2 spectrum. So in other words, if I assume that the background nonlinear time of the cascade is associated with the growth time scale of the instabilities, I get exactly my k to the minus 3/2 spectrum. So this is, I think, how to actually get the k to the minus 3/2 spectrum for supernova-driven turbulence. It's about the instabilities that form in these thin baroclinic layers. And this applies both locally and then through the inverse cascade that I was describing before, globally as well. So you can see how different this is from the Kolmogorov picture. Locally, I build up an entire spectrum based on those thin shell instabilities, and then through this inverse cascade mechanism, I bring it, imprint it on the largest scales in my galaxy. That is, the large scales care about the instabilities happening on small scales. Now, there's one final thing I want to point out before I summarize and conclude this colloquium, and it is, what is the nature of the driving scale if the driving is happening with an instability, which is driving on all scales, essentially. Now, I can take my relation, which I just derived very simply from equating the source term to essentially the thing that's feeding the turbulence, and I can take my RTI spectrum, which comes just from the Rayleigh-Taylor instability. I can plug this back in, and I get that the spectrum in which the modes are driven, the driving spectrum, not just a single mode that's being driven, the driving spectrum now goes like k to the 3/4, and that's exactly what I find in my data, where this peak scale is the thin shell thickness scale. So in other words, the way that supernova drive turbulence is not through one single bandwidth, not from a large scale mode, this abstract mode. It's from an entire spectrum that peaks at the thin shell scale and then goes all the way down to some truncation scale where the thin shell instability is growing its longest wavelength possible, associated with the spherical harmonics of the supernova. There is no driving scale. There is driving scales. There's driving spectrum. And that tells you that this scenario 2 that we talked about is also realized. Essentially, at the supernova scale, you're pumping energy across the entire spectrum of modes. So this is my last picture. This is what I want you to take away. This is what I want you to take away from this colloquium, is that the supernova essentially has this beautiful corrugated layer that drives vorticity associated with every single corrugation that's set by the instabilities happening in the layer itself. And then that imprints itself everywhere on the small scales, and through this inverse cascade to larger scales, you then imprint it on the entire galaxy. I think this is really cool. So let's summarize. Supernova-driven turbulence, and hence twiddle galactic turbulence, resembles nothing of the standard Kolmogorov model. Thank you very much.
Okay, questions?
I must be missing something, because if we adopt the ideal gas equation of state, P equal
Yes?
rho T times a constant, and if there was a temperature floor as a result of cooling, so that after cooling the temperature would be uniform, then rho is proportional to pressure. There is no barocyclic source.
Yes.
So the only way I can understand the driving of your vorticity is that somehow there is no temperature floor.
It's not about a temperature
No, but
floor.
I'm saying, suppose there is a temperature floor, you agree that P is proportional to rho,
Yeah.
right? So
Yeah.
then you don't get...
The baroclinicity comes from non-adiabatic processes. It's non-adiabatic.
No. Forget about terms, adiabatic or not. I'm saying if there was a temperature floor to the cooling,
Yes.
you would get P proportional to rho, and you wouldn't get the barocyclic driving.
You would get it on
How
all
do you
scales in which don't exist at the temperature floor.
Sorry? But if the
At all
temperature was
scales.
uniform, then P is proportional to
Yes,
rho.
if it's isothermal, then there is no baroclinicity.
There is no baroclinicity.
But this is not isothermal.
That's the point. That's my point. That's what I'm asking. So
Okay.
why is it not isothermal? Because if you had then I guess you should be able to see that somehow the metallicity drives you to a variety of temperatures. So.
I can show you this is not an isothermal simulation. This is a multiphase.
I know it's not, but
Yeah.
in reality it needs to be non-isothermal in order for your process to operate.
Oh, 100%.
So what is the temperature doing actually?
This is the phase space diagram of the galaxy, and you can see, you're essentially moving down this adiabat.
Oh, okay. So it's
Yeah.
not a flat bottom, but it's going down all the way.
It's very much not flat bottom.
Yes.
Yes.
Okay.
This has to be outside of the realms
so
of.
that's key, because otherwise.
Oh, it's 100% key. So
Yeah.
that's why you can do these same simulations, and then you pick an isothermal equation state. What it looks like is like boiling water. There is no turbulence generated. It's just supernova, or it's just sound waves expanding past each other.
That's my point. If it was thermal, you
100%
you would
agree.
get it.
100% agree.
Yeah, okay, good.
Yeah.
Thank you. Yes? I'm sorry I came in the middle, so if you answered this already, I apologize. But you just said like boiling water, and in boiling water, the bubbles very much interact with each other, and I couldn't tell from your pictures how
Yes.
much that interaction is taken into account or how much it matters.
It actually doesn't matter very much, which was very surprising to me because actually maybe this plot, actually no, this plot will show you better. So this is late in the simulation. So you're right to suggest that the supernova that I picked out here, I mean, I wanted just to show some very nice isolated-ish remnants. There's not strong interactions at this stage. I picked them out very, very early. But in the more general case, where you have a big turbulent blob of plasma, you can still see that they're rather, you can pick them out. They're not overlapping completely in these early stages where they build up this entire spectrum of modes. And that's the important thing. It's like early on, like at the cooling radius, they're building up all the modes before they interact with each other strongly. Yeah. I get this K to the minus 3R spectrum in the complete steady state where you have supernova everywhere, and I get it very early on when it's just an individual supernova expanding.
And I definitely missed this in the beginning, but what's determining where the stars that go supernova are?
So we've played around with a couple of prescriptions, but the one that I show most of my results are just the simplest prescription. You essentially have a scale height on either side, and you uniformly blow up supernovas everywhere in that scale height region. But we've messed around with you weight by the local mass density, so you're going supernova only in the density peaks, and nothing changes in this story.
Thank you.
Yeah.
Actually, I also got a question about this, but because this is very different from what people usually say about how turbulence is driven by supernova, which is mostly by these overlaps of bubbles,
Yes.
right? But here it can be like just a question of volume filling, right? So you have this background, which is not as intense as these bright spots, but it's volume filling. So if you compare like the total energies in these two different sources.
So the total energy, or the total baroclinicity rather, you find is in this steady state is 90% in these very low volume filling factors and 10% in the weak stochastic background through the shock interactions. And again, this is because the shock interactions can be non-isothermal as well, just any corrugated non-isothermal shock. So there is some vorticity generated, but I am still very convinced that it is actually, and this is due to going into the local supernova, grabbing them and doing the whole analysis here, that the entire K to the minus 3 half spectrum is happening from there, not from the background.
Well, I guess thank you for the nice talk. I guess part of my question was already kind of as I was going to ask about some of the variations that you made and the assumptions, and whether there will be some cases where you don't reach that final spectrum.
Yes.
So related to the locations that you're assuming.
I would say it's
the
really
energy that you are injecting.
it's the cooling function that is setting the cooling radius for the supernova remnants. And if you're in a plasma where the cooling is very inefficient, then these remnants can just keep expanding forever and they never go unstable, right? So really, I think the key aspect here is the cooling function. We've picked a cooling function that matches a classical galactic cooling function. But if you're in a different galaxy where the cooling is very inefficient, I think you never run into these instabilities. And actually, we see this kind of in some elliptic galaxies. The cooling is just inefficient. And they never undergo this instability. They just look like boiling water.
If this is happening at the cooling radius, the cooling itself is violently unstable,
Yep.
which will give you a big contribution. And in fact, there's a study of the Cygnus loop that shows that the contributions from the Vishniac instability, the thermal instability, and the shock running into pre-existing density inhomogeneities are fairly comparable.
Okay.
And it includes an estimate of vorticity.
Oh, nice. I would love to see this study. I don't know this study. That's really interesting. So I think the additional corrugations from the background will play a role, but I still am convinced, from just doing the calculations that it's not as important as the corrugations that happen in the contact discontinuity. But maybe you're saying that they're comparable.
Yeah.
Okay.
That's because of free cooling, or why is the cooling unstable?
The cooling is unstable as soon as the cooling curve turns over. So as long as it's steeply rising below about 100,000 degrees, it's stable. But once it flattens out, it actually goes down as a function of temperature. It becomes very unstable.
Yeah. Yeah. That's why this was actually quite confusing to us. I was showing you that you could essentially explain the entire sound speed spectrum just through adiabatic processes. But this spectrum does not, the thing about spectra, and something that you should always keep in mind, is that the spectra is non-local in space, and it's sensitive to the most volume-filling part of space. And essentially that means that you can have these regions of very strong cooling, which we're describing, actually catastrophic cooling in the thin shells, even though the entire galaxy is mostly adiabatic.
Yeah, but I can.
No, maybe you're gonna talk about it. What about magnetic?
So magnetic fields, very, very interesting. And let me just make a small comment on magnetic fields. And this is something that I'm working on right now. I won't be saying anything about it in the 3 talks I'm giving today. But this layer and this baroclinicity looks exactly like, Sand's proportionality constant, the BMN battery, right? And in fact, so this is the simulations I'm running right now. You can start with zero magnetic field, and you can generate it at this layer, which is very cool. It's weak, it's stronger than a lot of other astrophysical seed fields, magnetogenesis style. I think it's like 10 to the negative 16 Gauss or so. But then it couples directly to the turbulence you're generating in the layer at the same time. So it undergoes a turbulent dynamo immediately. So I think this is very interesting for magnetizing the early universe with the first supernova. I don't think it's, even in modern galaxies, they should be, all the supernova remnants should be producing magnetic flux through this term. But I don't think it matters for the background, micro-Gauss field. I think for early universe, a radiatively cooling blast wave will magnetize it through this process. And then I think everything that I've described to you, as in, we talked about inverse cascades. So then, in my mind, the magnetic field only has solenoidal modes, it only has incompressible modes, but it can couple to the background compressible mode that's being sourced by the supernova remnant. So in other words, you do BMN battery on the scale, you make it strong through the vorticity, and you bring it to the larger scales of the galaxy through the cascade. So I think this is very exciting for me.
Yeah, it would make sense.
Yes.
I just have one tiny observer question.
Yes.
Which is what do you want in terms of, to show that you're correct or not?
So there are a number of things that I want. I've made some predictions for the spherical harmonics of the supernova remnants, and we have been able to measure spherical harmonics of supernova remnants in the radio before. And this I want to compare to make sure that the instability, which has this imprint on the harmonics, has the same imprint on the observational harmonics. So this is something I want to do, which just kind of makes sure that the instability is happening. The next thing I want to, then it gets complicated. I can't do this on the sky, that's for sure. But what else can I do? There was one other thing that I wanted to do, but now I'll have to chat to you after the colloquium.
Yeah, we have. Let's thank James again. Yeah, James has a few more slots later today, so feel free to sign up for watch us. Continue the discussion.